Welcome to Parametric Equations. What we're going to be doing with parametric equations is actually separating x and y from each other and modeling them through a third variable that will most often be described as time, because that makes our lives a little bit easier. If we were in class, I would be taking a tennis ball or some sort of ball, maybe Olaf, I don't know, and I'd be throwing it at one of you. And we would be talking about what path it takes as it travels through the air. So if we were to do that and model this kind of two-dimensionally, it would have some sort of height, we'll say. I'm just going to let that be y when I'm talking about it. And I would throw it and it would kind of make an arc in the air until like maybe it hit the floor because I threw it bad and you didn't catch it. And we'd have something over here where this would be an x value which is equal to some sort of horizontal distance, right? And this is different than how we've modeled things in the past. Normally, when you're modeling stuff, like in the problem set, for example, we would do height versus time. And it would make this same path, but now we have a different variable here. So what's actually been happening for this scenario right here, and you've probably never really recognized it or realized it, but we always say something about that we're throwing this ball or we're throwing this object straight up in the air, which means that we're actually throwing it straight up and it comes straight back down. On this graph over here, visually what that would look like is it would still start right here and it would go up to wherever that point is and then back down, and it would never leave this spot on the graph because horizontally it didn't travel anything, right? If we're throwing something straight up in the air and straight back down, then its horizontal distance was 0. So what we're going to be able to do is now no longer just throw things straight up in the air. We're going to be able to throw them with a horizontal distance as well as a vertical distance. And when we do that, we're going to be able to find points along the graph that have both an x and a y, but they also have this kind of hidden t value or this hidden time. So it's at this point at a given time value. So we're going to be able to do some really neat things with this. And I hope you're kind of excited about it because it's really cool, the stuff that we could do. Now that we have an idea that we're going to have some sort of xy point at a given time value, we can start coming up with new equations for things. I can't spell or write the word time apparently. So what we're going to do is we're going to break x and y up. We're going to say x is now equal to some sort of function of time, and y is going to be some sort of function of time, but they're not necessarily the same function. So typically the way that we'll write this is we'll say x of t and y of t. So we're separating x and y from each other, but they're still connected by this t value, okay? This t value, this is referred to as the parameter. And there's something else that we need, which is that we need an interval. Okay, so we have an I value, which is going to be the interval of the parameter. So every single set of parametric equations is going to include three things: an x equation, a y equation, and an interval. Every single time. So for our first example, we're going to graph this parametric equations. So I have x is defined by t squared minus 2, and y is defined by 3t, and we have the interval is going from -3 to 2. So over here I have a big old table created for us as well as the graph, and I've just picked whole numbers that just go between -3 and 2, and I don't need that last one there because the interval stops. And I'm just going to plug values in to the equation. So if t equals -3, then I get 9 minus 2, and that's going to be 7. And I'll just continue with all the x values. So I plug in -2, and that will give me 4 minus 2. I plug in -1, and I get 1 minus 2. I plug in 0, I get -2, then -1, and then 2. I'll do the same exact thing for the y value, so I'll do 3 times t for all of them, so that's going to give me -9, so I'm doing -3 times 3, -2 times 3, -1 times 3, 0 times 3, and so on. And now all I'm going to do is just plot the xy points, okay? So I'm sure this is going to be thrilling to watch me plot points. 1, 2, 3, 4, 5, 6, 7, and then all the way down here to -9. Now what I'm going to do is I'm actually going to label this as the start point because it's when the interval starts. It's the smallest t value. Then I'll plot the next one is at 2, -6. 2, 1, 2, 3, 4, 5, 6. Okay. And as I connect these, I'm going to put a little arrow right here to signify that if I start here, I'm moving in this direction. Okay. And the next point, I'll do -1 and then -3. So that's going to be right here. And I'm just going to plot a bunch of the points now before I keep attempting to connect them. And then 1, 2, 1, 2, 3, 4, 5, 6. Okay. And this is where I'm going to end. So here is what this graph looks like. And I might put these little arrows all over the place. So I'm starting here and it's traveling that way. So the reason we have to put start and end is because generally speaking, t is referring to time. So we want to know at what time did we start, like where were we, and at the ending time, where did we end? And then these arrows are signifying which way we're moving, which isn't really necessary if we label start and end in this case. But what if we were starting here and we were going like that and ending back where we started? So if our start and end are at the same point, we don't know whether we went counterclockwise or clockwise. So we would definitely need to include some sort of arrows to signify where we were starting and stopping if it wasn't as clear as this. And congratulations, that's our first graph of a parametric equation. So we just created a table, plugged in the t values based off of the interval, plotted the xy points, labeled where we start based on the smallest t value, and included the direction by basically saying as we connect these xy points, that's going to signify the direction that we're traveling in. This example doesn't really work during distance learning, so I'm going to kind of talk you through it, and then I'm going to pull up the answer key and show you what it looks like. So what we would have done is I would have split the class up into groups of 4, where each person would pick a different one of the 4 graphs on this page. And I would ask you to graph all of them. So you can see that they all have different equations. Okay, you have, x equals 4t squared minus 4. Over here, it's t squared minus 4. This is 4t squared plus 8t, 16t squared plus 16t. So they're all different equations. All the y's are different. And all of the t values are different for the intervals. So what I'm going to do now is jump over to the answer key so that you can see what it would look like after everyone in the group had graphed each one of their assigned graphs. So here's the answer key. All I did to find all of these answers is I just plugged in the t value into the 2 equations and found what the values were. And here's the graphs I get. So let's just look at these first 2, because they look pretty much the same to me. Can you notice what's different about them? I'm hoping you noticed that this one, it starts here and it travels this way around, whereas this one starts over here and travels this way around. So they're starting and stopping at opposite points. Now, there's another thing that's happening, which is that this one only takes 2.5 seconds to start from here and go all the way around. I'm just picking seconds arbitrarily. I have no idea what the time frame is, and we're ignoring the fact that negative time doesn't make sense. And here it takes 5 seconds. So this one takes 2.5 seconds, and this one takes 5 seconds in the opposite direction. So visually, if we didn't have these arrows here and we didn't have the t interval, these graphs would look identical, which is why we need parametric equations, because we need to be able to model different situations even when they appear to be the same. If we continue on and look down here, it's the same exact thing. We have them going in different directions as some of them, and we have different time frames again for all of these ones. So essentially what this would be modeling is someone maybe like walking from one part of the classroom to another, and maybe they had to avoid a desk that was like right here, and this is the example I would be doing in school, is I would be walking from one part. So it takes a different amount of time or a different direction for some of these, for each one of these 4 examples. And we would not be able to capture that if we didn't have this third variable of time. We would just think that someone walked in this path, and we would have no idea how long it took them. So parametric equations allow us to make models of things that take into account the timing of them as well, which is really powerful when we're talking about modeling real life, which has time in it. Next set of questions are all going to be on something called eliminating the parameter. Now remember, the parameter is t, so what we're basically doing is eliminating t, and we're combining these equations back together. So we're switching from a parametric equations where x is defined by t and y is defined by t to rectangular equations where y is defined by x. So for the first one, we have x equals t plus 1 and y equals 2t. I'm going to ignore the interval for a second. And I'm just going to solve one of the 2 variables, it doesn't matter which one, for t, and then substitute it into the other. So for here, I will just subtract that 1, so I'll get t equals x minus 1, and then I'm just going to substitute it in. So y equals 2x minus 1. And if I wanted to, I could simplify that by just distributing it through. So here is what the 2 parametric equations are as a rectangular equations. So together, these 2 things are just going to visually create a line. And these are part of the questions I'm going to ask you, is basically eliminate the parameter by putting it back into just y equals x, or that type of form, and then identify the equation. Now, it's not always as easy as it becoming a line, so we do occasionally have to do a little bit of work to figure out what type of equation it is after we've put it in rectangular form. So let's get it into just xy, meaning we've eliminated t. And in this case, it's going to be much easier for me to take this equation and say that t equals y over 3 than it would over here, because I would have a plus or minus if I tried to solve for t, and I don't want to deal with that. So I'm going to solve this one for t equals and substitute in here. So I'll have x equals parentheses y over 3 squared minus 2. If I want to just simplify this a little bit more, I'll get y squared over 9 minus 2. And I think we could actually keep going, because I don't know if a lot of you would recognize what this equation is yet. So I'm going to, I think, add the 2 to the other side. So I'll get x plus 2 equals y squared over 9, and then multiply the 9. So I'll get y squared equals 9 times x plus 2. And that's good enough for us, because I can now recognize this is going to be a conic section parabola. Now I know what you're thinking. Oh my gosh, I've forgotten everything about conic equations. So let me give you a quick crash course on the things that are necessary for you to remember in this particular unit, which is basically you need to be able to recognize the equations of what they are. So for parabolas, we have the base equations where like x squared equals 4py or y squared equals 4px. So basically, if you have a single thing squared, either x squared or y squared, it is a parabola. Done. For ellipses, which I always say as eclipses when I'm not paying attention, in this case we have x squared over some value and y squared over some other value, and they equal 1. And the important thing here is this plus sign right here. So basically, which isn't 100% true all the time, but generally speaking, if you have x squared over something plus y squared over something equals 1, so basically we have an x squared plus a y squared, we know that's going to be an ellipse. Now, we do have a subset of this one, which is that if a and b are equal, then it is a circle. Last one, we have hyperbolas, and very similar to the ellipse, it's going to be x squared over something minus y squared over something, and we can flip-flop these around, so it could be y squared over something minus x squared over something equals 1. And in this case, basically you have 2 things that are squared, and one of them is being subtracted, hyperbola, two things squared, added, ellipse, only one of them squared, parabolas. And there you go, that's your crash course on what you need to remember about conics. For this last style of eliminating the parameter, there's actually a trick here. So there's no easy way to isolate t in either one of these without using inverse trig, and that gets a little bit sloppy when we start doing substitution, so we really want to avoid that. So can we think of any sort of relationship between sine and cosine, or an equation that we know for a fact is true, that would maybe allow us to do some sort of other substitution? Should I give you an awkward Dora the Explorer pause now to see if you can come up with that equation on your own? No? Okay. Then I'll just jump into it. First thing I'm going to do is isolate the cosine and the sine. So I'm going to have x over 3 equals cosine t, and y over 3 equals sine t. Next, I will square both sides. So that's going to give me x squared over 9 equals cosine squared t, and y squared over 9 equals sine squared t. And from here, I'm going to use our favorite equation, which is that sine squared plus cosine squared always equals 1. In this case, sine squared is equal to y squared over 9, and cosine squared is equal to x squared over 9. So I get this equation right here. I can multiply the 9 to the other side, maybe do a little bit of rearranging, and I will end up with this, which I'm pretty sure we all know is a circle. So whenever we have sine or cosines up here and we're trying to eliminate the parameter, your goal should be to identify which one of the Pythagorean triples it's going to be, because it's probably going to be one of those three. For this last one, we have someone walking along a horizontal line with the coordinates of their position in meters given by this equation, s equals point blah 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 blah. And we're just paying attention to this for the first 12 time units, and I'm just going to use seconds to make our lives easy here. And what we want to do is use parametric equations and a graphing calculator to help simulate what this motion actually looks like. So I have my graphing calculator open over here, and the first thing we're going to do is hit mode. And in mode, what we're going to do is switch ourselves to this parametric one. That's down here. So we're going to move off of function and into parametric. And this is going to allow us to do parametric equations in our calculator, which is really super useful. And while we're actually on this menu and we have function, parametric, polar, and sequence, that actually corresponds to what these values are here that you maybe have never noticed or paid attention to, but where we always hit x in the calculator, that's x because functions are always defined by x. In parametrics, things are defined by t. In polar, which we'll learn next unit, things are defined with a theta value, and sequences and series, which you learned last year, used the letter n for everything. So this is kind of neat. We're actually starting to explore some of the other features of our calculator. So when I've put it in parametric mode, and I jump up here to y equals, now each y equals has an x and a y, and when I click this button, it's now time that goes there, t, not x like it used to be. So it tells me right here that this is the horizontal line. So x is the thing that models horizontal lines normally. So let's put this in for the x equation. All right, so once we get this equation in here, if I go and hit graph, nothing's going to show up here. And that's because in order for parametric equations to work, we need to have both an x and a y. So I don't know what the y value is. That's the vertical distance. So let's just pick a number, any number. So I'm going to pick 5. And I just want to stress that I'm making that number up right now. And that's because what's happening here, someone is walking back and forth like my mouse is doing right now in a horizontal direction, and the vertical value isn't changing. So by me picking this random value of 5, I'm just saying like, okay, I'm right here rather than being at 0. That would maybe be right here on top of an axis. It'd be difficult to see what was going on with it. So before I hit graph, let's play around with the window a little bit because the window looks different now. We now have t values in addition to x and y mins. So for the t min, I'm going to leave it at 0. And for the max, I'm going to make it 12 because that's what they told me to do here. And for the t step, we're going to play around with this in a little bit. But for now, let's make it 0.1. I think we're also going to need to change the x-min. So I'm going to maybe make that negative 15. Let's leave it as 10 and leave everything else the same, and we'll see if that works. So you hit graph. If yours is super fast like mine, it just immediately showed up, and that was that. So can't see anything else. What we can do is play around with that t-step value and hopefully get it to slow down a little bit so that we can actually see it graphing as it goes. So I'm going to change this t-step to 0.01 and hit graph, and you can still see it went way too fast, and that's because this calculator is running on my computer, which has a lot of processing power. So let me make it a little bit slower. Your calculator will probably cry if you do this, so don't, maybe. And now I can see it going really slowly. It goes here and it reaches this point, and then it stops showing me stuff, but it's still graphing because that thing is going on there. So that's interesting. It's actually still graphing, and it finally stopped graphing. So I'm going to jump back to what most of you probably have in your calculator still, which is 0.1. Let it just graph itself super quickly and hit trace. So at t equals 0, that's where I start. Now, if I try to move myself this way, which is how we visually saw it when we graphed it, and I try to hit this arrow, nothing happens. And that's because these arrows are controlling time, and time starts at 0, and we can't go backwards from 0. We can move forwards in time. So as I hit this arrow here, the graph is moving to the left because the time value is increasing, which is changing what the x and y points are. So you can see as I continue progressing through, we're moving left, 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 and at a certain point somewhere around here, stops moving, and now we're moving to the right. And we can't really see this when we're all in a straight line because it's too difficult visually to overlap. And then what's this? Oh my gosh, it changed directions again. So what we got here is this value of 5 is doing good to accurately represent what's happening, which is keeping us on a horizontal line, but we can't actually see anything. So what if we changed y to be time? And I'll now need to change my window for the y values. I can leave it at -10 if I want. I'm going to make it 0 to 12. I'm going to make this, I don't know why that did 0, 12, to line up with what t is, because I just said y equals t, and let's actually just hit graph and see what that looks like. There we go. I'm going to increase the y values in either direction so we can see the start and finish a little bit better. So here we go. This is a visualization of what this path was. What we had originally was this one if I like squished it down. So what we just did by allowing y to equal t is essentially we allowed the graph to move vertically over time instead of remaining stationary along this horizontal line. And the easiest way I can explain what's happening is with this visualization of like a seismograph that you've seen in any movie in the world. What we basically have happening is it starts and then this thing moves. And as this thing is going back and forth in the horizontal direction, this piece of paper is moving, so it appears as though it's traveling up or down this piece of paper. And that's exactly what's happening here. We basically have moved the y value up, or a piece of paper behind our pen as we were tracing sideways. And now we can see this visualization of where these changes in directions occur. So we can see right here, stopped going to the left and now started going to the right. And then right here, we can visually very easily see that they've now changed directions again and are walking back towards the left. So when we hit trace and we go to find those values, it's much easier to visually see what's going on. And we have one last thing that we can do, which is we're talking about horizontal distance here. So we can look at these x values and see at what point do they stop going left or negative, and do they start to get a little less negative. So here is 3.9, which is negative 9.91, and this is now less negative than that. So I'm pretty sure that at time 3.9, this person is changing directions. Now we could get more accurate later on, and you could definitely get more accurate if you were in calculus, but for now this is good enough for us. And then the next one is way over here. I'm doing the same thing. Now I'm going to look at when do these x values get closest to 0 as I'm going here. And I think it might be right negative 1.2523, 2375. Yep, I think it might be right here at 9.5 is the closest this gets to 0. So this person changes directions at whatever those two numbers were that I just said, 3.9 and 9.5. All right, that's it for today. You do not need to do the practice section today. We're separating this stuff out because it's a little bit harder. So that way you can kind of rewatch the video as needed to make sure that you understand the basics of this stuff. And then next class's activity will be to do the practice section. And I'll probably have a video for it because I imagine you won't even be able to get through question 1 without having some questions. So enjoy that. So before we do that, let's just remind you of a few things. So here, I just have a lovely little axis here. I'm going to make this the height and this the time. And what we're going to do is model what would happen if I had actually thrown this ball up in the air or thrown it at one of you, which is what I would have done if we were in school together. So if I throw this ball, it makes, generally speaking, a parabola-like path as it goes through the air. So we could model that, depending on how tall I am. It would start somewhere up here in the height, and then it would go like this until it hit the ground. And this is how we've always visualized it. We always use that equation, you know, h of t equals negative 16 t squared plus initial velocity plus height. And that's always how we've modeled these for the past couple of years that we've been doing these. But this isn't what actually is happening. When I throw the ball to someone, this axis right here is not time. This would actually be the distance that I'm throwing it. So we would need to change this to be x, so that when I throw this, I now also can see the horizontal distance that it's traveled. So that means that at any given point, there's both an x and a y, or height value, at some given time. Right, so I throw it in the air, and at 0.5 seconds, we can figure out what are the x and y values at 0.5 seconds. So we're separating the graph out. We're no longer letting this be time. We're now letting it be x and y with kind of this third hidden variable of time. That is the greatest noise ever. 1, 2. What if I just made you sit here while I typed it all in and forgot to edit this out?